Here are some simple practical operations for data collection, signal generation, and algorithm verification. First, we make a simple entry-level FM receiver. The reception range of USBRP is 30 m6 GHz. FM is generally in this frequency band of about 100 meters, so well within the frequency range that USBRP can receive. We can acquire it by receiving and demodulating the signal in space. We broadcast data. This is a demo that is easy for everyone to get started with. And then we're going to go and do some of that. And then this is a flow diagram. Then this is the X310 USBRP produced by Liu. He is responsible for receiving space and signals. Then connect to this computer through a network cable. Then on the computer we loaded GNU Radio. This UHD module is responsible for configuring the hardware. Then what about after configuration? After configuration, after he receives the signal, including configuration information, center frequency, amplification gain, etc. Then he downconverts the signal in space to a baseband signal. Backwards processing, IQ data comes out. The data that comes out is already the IQ data of the baseband. What about after getting it? We need to first turn the audio signal into a 48 kHz sample rate signal. Because the operating frequency of the sound card is 48 kHz, so we have to go through a series of processing. Suppose we want to vary the sample rate. Because the sample rate is currently set to 768,000. It also needs to go through a series of up and down variable sampling rates from 48,000. And then, after the sample rate conversion is completed, we're going to use the FM receiver to demodulate the FM signal. After the demodulation is completed, it will be sent to our sound card for playback. The reception of the FM signal is completed. Meanwhile, we can call some of this oscilloscope to observe our signal waveform. The flow diagram is already running. This is the process we are running now. You can lower the volume. Sound on to 50. Okay. The current reception frequency is 91.6 meters. This is a traffic radio in Xi'an, China. We can switch frequencies. Change the channel 98.8 trillion. It is also another music broadcast in Xi'an. It's an ad now. You make your voice louder. Then we can switch to another channel. 30 m6 GHz. We can get it all. It's 95 meters now. This is book radio. We can exchange another 89.6 meters. Now you can receive all the FM broadcasts in the space. So the next step we're going to do is actually do the ADS-B reception. This ADS-B is a signal form for our civil airliner to broadcast to the outside world. What about a commercial airliner? It keeps broadcasting signals. What's on the air? Just broadcast who I am, where I am, my altitude, my speed, flight number, etc. So ADS-B, the whole protocol is open source. So on the ground, once we demodulate the information on the receiver, we can get information on commercial airliners flying within a 300 kilometer radius above us. After this information is demodulated, it is used through the API of AutoNavi Maps. So what? You type this in, then we can see on the AutoNavi map the radar signal above us, the commercial airliner. And then we went into practice. Same thing, or use the LW-X310 to receive. Then EDS-B is demodulated in detail through several demodulation modules of EDS-B. Finally, we import it into the AutoNavi map through this interface. Then on the AutoNavi map, we can see which planes are flying over Hebei and other information. Moving on to the second practical step, signal generation. We become a frequency hopping signal. Frequency hopping is a means that we use a lot of anti-jamming in this communication. Then it avoids interference by constantly changing the frequency of the carrier wave, resists monitoring, etc. We can generate a frequency hopping signal using SBRP. And you can see that the signal bounces through space. And actually feel it. Okay. Now let's take a look at the actual operation. This is the frequency hopping module. The core module is this. There is a lot of code in this module, not just a module. Then frequency hopping is achieved. Finally, send it out. We can also receive and demodulate frequency hopping signals when sending them out. Let's demonstrate sending first. We're hopping the frequency. You can see that our frequency hopping signal is constantly hopping in frequency. Then send it to the space through SBRP. We can also see him bouncing back and forth in the 800 meters band with our spectrometer. It's the same as ours. The central carrier frequency is 800 meters. This is the generation of frequency hopping signals. After the generated signal is collected, you can receive the frequency hopping signal. Let's take a look at the next practical operation. Next, we want to generate direct sequence spread spectrum, another anti-jamming signal. You can take a look with me. So this is a transmission of our DSS's direct sequence spread spectrum. We also made a local reception. It was picked up locally and demodulated. This is the source. We sent 12,345. And we send out the signal. After adding the frame header to spread the spectrum. This is mSeq1, our self-generated spreading sequence. We can preset a lot of variables when we execute this development. Just call it directly below. The source goes through a series of transformations into a data stream. Because we want to perform QPSC modulation. So we're going to split the 8 bits into 2. That's 1 byte every 2 bits. Incoming QPS modulation. After the payload passes through this. And here we go for QPSC modulation. This is the 4-digit constellation chart, the constellation map. Then add a header after debugging. 2 together. What happens when we put it together? Enter the spread spectrum module together. Spread spectrum is actually a kind of filtering. But you're interpolating the length of the spreading sequence. After spreading the spectrum, combine this data stream. This has added a frame header. Combine with the frame header. The frame headers are also generated using VCG sequences. What about after generation? The frame header and the data matching are combined to form a frame. 1 frame later, we'll send it again. After sending it out, then we do a simple reception and look at the constellation. You can see the effect first. This is the spectrum of the signal before we spread the spectrum. This is the signal spectrum after spread spectrum. You can see the signal, it has a spread spectrum, a broadening of the spectrum. And this is the constellation of the header. The needle can be prepared without BPSC. And this is the constellation of our payload. This is our demodulated signal. It's 12,345, 12,345, 12,345. This is our spread spectrum signal. What do we do next? Let's move on to the next practical exercise, algorithm verification. The first one we do is this spread spectrum detection. One of the advantages of spread spectrum signals is that they can send signals with very low signal power. So in practice, what if we need to do signal detection? Suppose that although the power is very low, the signal still needs to be detected. The detection of low power or weak signals is a challenge in itself. But we can use the cyclic stationary statistic. It is to use the cyclic stationary characteristics of the cyclic signal to detect. This belongs to this phase detection. In fact, it also belongs to the scope of radio. A typical spectrum sensing or phase detection algorithm. Then let's look at the specific implementation. So let's go here and look at the flow diagram for cyclostationary detection. We first generate a DSS signal. It is similar to the DSS picture we just had. We first generate a peak spread spectrum signal. Let's run first. On the receiving end, this is the sending US BRP. This is the received US BRP. The cyclostationary feature is a specific feature of a signal. The principle of cyclostationary detection is that some modulations will appear different or have a spike at different carrier frequencies. This is a fundamental feature of cyclic frequency detection, although its signal power is very low. But at certain frequencies, in certain debugging methods, a spike occurs. As long as there is a spike, we can determine the presence or absence of a signal by determining the threshold. Let's take a look at the transmitter first. After modulation and spread spectrum modulation, the spectrum of the original signal has been spread out very widely. And then we run a cyclostationary detection algorithm on the receiver. You can see that there are some spikes in certain frequency bands. In fact, in our demo, the signal power is not particularly low. However, this does not affect the verification of the algorithm. We have also tried a lot of signal power, such as putting the signal power very low, and our spikes are still obvious. We can draw a gate line by take n times the mean or half the maximum as the gate. The presence of a spread spectrum signal can be easily detected. Let's do one last practical verification. It is OFDM. OFDM is probably the most widely used physical layer modulation we currently use. A transmission mechanism that will be used in Wi-Fi, LTE, 4 grams, 5 grams, and future 6 grams. Therefore, US BRP must support a transmission of OFDM. The principle of OFDM is multi-carrier. If you don't know the principle of OFDM, you can learn it according to this process. We are now mainly looking at how to achieve. This is a transmission from OFDM. The sender is messy. And then we go from the source through a series of encodings, channel encodings, modulation maps, and a series of framing, subcarrier assignments, cyclic prefixage. Finally arrived at USBRP, a very complex OFDM process. Many modules are integrated modules. It actually contains a lot of other modules, such as the spread spectrum module just now. This module is actually a submodule of the spread spectrum module just now. Then after he clicked on it, there are actually many modules inside. So our flow graph often looks simple. But it actually contains a lot of modules. Of course, modules like these are some modules that come with the system. There are actually a lot of code and modules in it. Okay, this is our launch terminal. Then the transmitter also goes through a series of reverse processes. It includes complementary frames, connected frames, and a series of FFTs. Final demodulation to final display. The transmitter has started to operate. You can see a waveform at the transmitter. We sent a duplicate 123. This is the signal waveform. Now the receiver is up and running. You can see that the final demodulated signal at the receiving end is also 123. This is the time domain waveform, the constellation. Okay, this is a simple hands-on demonstration of OFDM. Thank you very much.